I'm a research scientist at IBM, based on New York City. Well, technically not New York City. It's Yorktown Heights, which is like 60, 70 miles away from it, but pretty close to New York City. In any case, what is my background? So I did a double major back in the day in computer science and aerospace engineering. I then moved to the US for a PhD in aerospace engineering, actually. And then you're like, why are you not making rockets and SpaceX instead? Why are you here, right? So the reason I'm here is my PhD was actually based on building chatbots for engineers building satellites, right? So I did a lot of work with not a lot of resources, because when you try to ask an aerospace lab to buy you a GPU, they're like, why do you need a GPU? You're making not doing 3D graphics or anything. You don't need a GPU, right? So I had to make do with what I had, and I had to optimize models a lot to make sure that they were running well with very not good hardware, right? And that landed me a job at Meta eventually, and with the layoffs, they hit me as well. And then I ended up at IBM doing basically the same work I was doing at Meta, which is working on PyTorch and optimizations for models. And that's why I'm here today. Just going to be talking about how to optimize models, specifically for vLLM. So right, let's get down to the talk. What is the objective here today? So the first thing you need to know is, well, we want to squeeze the most performance out of a model, right? We run a model. Oh.
It's okay.
Right.
I'm just going to turn down the mic.
Okay.
No.
Okay. Can you still hear me? Okay. Sure. All right. So we want to squeeze the most performance out of each row passing the model, right? But first of all, we need to define what performance is, right? In a case of a language model, usually what we measure as performance is two different things. One is the latency, which is how fast you can generate a token. So every time you get a prompt, and you want to generate the next token in that prompt, which is how our language models work, you want to know how fast you can do that, right? The other thing is throughput. Usually, if you're a company that is selling inference for any kind of language model, you want to use your hardware to the maximum, right? And that usually means maximizing the throughput, which is how many tokens can you get out of a single machine for a certain amount of time, right? Usually, you measure the tokens per second. These two things are usually they are related. Better latency can mean better throughput, but that's not always true. Sometimes you can get very good hardware optimization that will work for generating a single token, but will not scale well to generating 32 tokens at a time or 64 tokens at a time, right? Which would make your throughput much better. And that means that you have to play a game of do I use this optimization, or what does my workload look like, so that can I get everything running with a maximum latency and throughput at the same time. Of course, there's myriad ways of optimizing models, and today I'm just going to be talking about one, which is the PyTorch compiler being used to reduce the latency of vLLM custom CUDA kernels. So what is torch.compile or a torch compiler? I think it was about 2 years ago, and if someone is here from Meta, please correct me if I'm wrong. But it introduced in PyTorch 2.0, the first stable version. Torch.compile is basically a compiler for machine learning models. So you can get a machine learning model defined in Python, you can see in the, hopefully you can see my pointer, yes. So defined here, you have a model in Python, and then the idea is you want to convert that into something that some kind of AI accelerator can run. It can be a GPU from NVIDIA, it can be a GPU from AMD, it can be a CPU from Intel, it can be any of AWS Inferentia, it doesn't matter, right? And the idea is, because going from Python to a machine code is not a very straightforward process, they do the same thing as most other compilers do. They define a set of intermediate representations, each one closer to the hardware, and then they define a set of translations from Python to the first IR, which is known as the FX graph, and then from the FX graph to the next IR, which is the A10 or the prim IR in PyTorch in this case, and then there's another lowering from this A10 IR or prime IR down to the hardware, which is either Triton kernels or CUDA kernels, or depending on the hardware you're running, right? And that would be what's known as torch inductor for Triton in this case. The good thing is that it can, as it was defined and designed in PyTorch, it was designed for both training and inference, because before torch compile, there were other compilers out there. The issue is that most of them were only for inference. This can also be used for training, although in this case of vLLM, of course, that's not the case. We're not worried about that. And of course, the main advantages are, it's open source because it's part of PyTorch. They have pretty concise APIs. It is flexible in the sense that it supports things that back in when this came out at the beginning, other ML compilers didn't have, like support for dynamic shapes, you can grow your tensors and this compiler will adapt. You can compile a model that sometimes fails to compile, and then the compiler will just break it in different submodels and run each submodel at a time before between the breaks and everything, which other compilers would just be like, no, I'm not doing that. And it's pretty easy to add new hardware. All right, so what is pitch attention? They asked me to introduce this a little bit because I'm the first speaker today. So this is the kernel we're trying to optimize, right? And this is moving a little too fast to actually explain what's going on, probably. Oh, but the idea is when you usually do a donut transformer model, there's an operation in there that's called attention, and the idea is you get three things: the query, the key, and the value, and you need to multiply the query and the key, and then apply a softmax operation on that, and then multiply the result of that operation times the value, which is two matrix multiplications in a softmax operation, pretty much, right? Now, most attention computation and before pitch attention required one thing, which is that the query, the value, and the key were tensors in the GPU memory or whatever you were running and they were contiguous. So you had to have every single token in a sequence together. That's fine when you have 256 tokens or 512 tokens. When you have 40,000 tokens on your query or your key or your value, contiguous space of that size in the memory starts to get a little scarce. So that's when something like pitch attention, which allows for this computation attention to be done with blocks of memory that are not contiguous in memory, is where you can get an advantage here because you can just use small spots in memory that you can just take from, and then the pitch attention kernel, which is written in CUDA in this case, will take care of multiplying the right places in memory for you and making sure that the attention you get at the end is the same result or similar enough to the other attention kernels, let's say flash attention or the original attention implementation, for example. And vLLM folks, if I messed up here, please correct me. But yeah, they say it's okay. All right, but yeah, that's basically what we're trying to do. So the way this currently runs is you have your PyTorch code, and then at some point you call a function that's called pitch attention v1 or pitch attention v2, and then something similar to this gets run on the GPU, right? So when you try to incorporate that in torch.compile, the torch compiler needs to, in some way, understand what this means to mix it together with every single operation every single operation you're doing in the GPU or any other accelerator. Right? You can have matrix multiplications before, or tensor views or tensor reshapings or concatenations, and the torch compiler knows how to work with all these things, right? What it doesn't know is how to work with pitch attention. And there was an attempt to actually make vLLM kernels like pitch attention be understood by the torch compiler, but there were some issues, right? The first issue is that the PyTorch compiler is actually just in time. What that means is that you cannot in C++, you have your code, you compile it, and then you get an executable, and then you can run that executable forever, right? That's not the case with the PyTorch compiler. In the PyTorch compiler, every time you start vLLM or any other software that compiles a model, you have to compile the model again, and this adds a significant amount of time to starting vLLM, right? Because computation is not a free process. So in the case of vLLM, loading a single model would take between 2.5 to 6 minutes of just from when you start running the program to when vLLM starts running and being able to serve tokens. That seems fine, but right now probably vLLM's at the time is around seconds and not minutes, right? So this is a significant amount. Second issue is that the PyTorch as a library only has operations that get inputs and then spit outputs without modifying the inputs. The issues that vLLM kernels in general actually are in place, which means that they get inputs, they don't return anything, but they modify the inputs in place. So there's the torch compiler doesn't know how to understand that, or didn't know how to do that. And then finally, the PyTorch custom ops API had issues on how to there's a lot of overhead when you like to launch this custom kernel with the PyTorch API to do it so that the compiler understands. This adds a lot of overhead that's unreasonable, especially for something like vLLM, which is very particular about like having the least amount of latency possible for the model, right? All right, so point one is still not solved today. There is something called torch export that some people are working on at Meta that should solve this point one, which basically lets you compile the model and get an executable and then just run that executable. But until that is stable and easy enough to use and works well with all these models, we're just going to focus on the second and third points. So how do you launch custom kernel efficiently with torch.compile? So the way it usually works is like torch.compile is actually capable of like, when you have a function in Python that calls another function, that calls another function, it's capable of like removing all this call stack overhead and just creating a single function or like a piece of code that can run all your model without any overhead, right? The issue is that you need to teach torch.compile how to do that with your operations because it knows how to do that with the PyTorch operations, not any other one. So then you need to do three things. And again, if there's anyone from Meta here that worked on this, do feel free to correct me if I'm saying something wrong here. But thing number one is you need to tell the torch library what inputs and outputs your function has. You need to tell PyTorch how the outputs depend on the inputs in terms of shape, type, etc., etc. And number three, you need to change your function to actually return something because if you don't return something, PyTorch will consider that function to be dead code, and then just the compiler will remove it from your code, pretty much. Because if you're not returning anything, what's the point of calling something, right? Because again, it assumes that everything is returning something by default. So this is the code for step one. You just define like this library, this storage library object with whatever code you want, which is in this case page attention, of course. And then you define a function. I'm using another function that vLLM has, which is called reshape and cache, which is the one that stores your new keys and values to the KB cache, the page KB cache with like this like non-contiguous storage blocks, basically, right? I'm using this one because it's a very simple function that is easy to show in like slides because the page attention kernel has like twice as many parameters and like a lot more code and everything, so it wouldn't fit as well here. But the idea is you define the function like this, like it's a shape and cache. It has like 5 different inputs. They are all tensors, and then it returns a pair of tensors, which in this case are the key cache and the value cache. And then on step two, which is telling it how the outputs depend on the inputs, we're just saying, okay, the key cache and the value cache are basically the same as the inputs as far as like shape and everything is concerned, but you need to make sure they are contiguous in the memory, which is how currently vLLM defines it, right? And then last but not least, you need to tell PyTorch how to call the vLLM kernel that is in place and turn it into an out-of-place kernel, like something that returns some value, right? So that is like this last part here, step 3, in which you define, ensure everything is contiguous just in case, because sometimes the torch compiler likes optimizing memory layouts, and sometimes that means making contiguous memory non-contiguous if the operation you're calling can accept it. In this case, page attention does not accept non-contiguous inputs, so you need to make sure they are contiguous. Then you call the original function, which is this cache ops.reshape and cache. This is the C++ CUDA kernel that these guys developed. And then you just return the key value, the key and the cache value. The key and the value cache, sorry. Now, that's not it, though. So remember how I mentioned like there's like a bunch of intermediate steps in between the Python code and the machine code, right? What I just did just covers the first 2-3 steps, basically. But there's still the step of like going from the torch API, basically, intermediate representation, to the actual Triton kernels or like inductor code general, code that gets actually run on the GPU pretty much, right? The way you do that is you have to register something called a lowering, which is what inductor understands as like, this is what needs to happen when I compile this function as part of everything else. How do I optimize this function, right? In the case of custom CUDA operations, like flash attention, or like page attention, or reshape and cache, things that basically cannot be expressed in terms of other PyTorch operations. You just say, okay, I'm gonna fall back and just trust it as a black box, pretty much, right? So this is the way to say, inductor, please treat my function as a black box. Just call it. I'm gonna tell you what interface it has and what things are important about it. But other than that, just trust whatever CUDA C++ code is running to just be the most efficient way to do this. So the way you do it is, and I'll go to what this page attention kernel object here in Python looks like in a second. But basically, you just say, okay, I'm calling this page attention reshape and cache function with all these parameters. And I am mutating both the key and the value cache. So like these two things are going to be, the memory is going to be modified, so please do not use that memory for anything else. Because, sometimes you can, PyTorch will try to also optimize that out. Like, if you can reuse memory for something else while this is running because you already copied it somewhere else, it will do it. So this is the page attention kernel object. So as you will see, it inherits from something called the fallback kernel, which is basically the way of, again, telling Inductor that this is a black box and it should treat it as a black box and just trust me to run this the best way possible, right? You will see a lot of code here. A lot of this code I just copied from the only other operation in PyTorch that is also in place. So when I said like PyTorch, all operations in PyTorch are like something that gets some inputs and spits some outputs, I lied. There is one exception to that rule, and it's the distributed operations. So let's when you have like two GPUs and you want to add together the results from the same tensor and two different GPUs, you call something that's known as all reduce, right? The all reduce kernel is the only operation in all of PyTorch that is also in place. So of course, the PyTorch developers, when they add support for all reduce and like all these other all gather, scatter reduce, and all these other operations that are like multi-GPU operations in PyTorch, they had to add a bunch of like tooling around them that now I'm taking advantage of to make all these in-place kernels in vLLM work as well, like the same way they use like for all reduce and everything else. The only issues that there's two things I'm using here, the non-layout here and the mutation output here. These two things are not available in PyTorch 2.1. Good news is PyTorch 2.2 just released yesterday, and those two things are available in PyTorch 2.2. So you don't need to run on nightlies anymore to actually take advantage of this particular feature. So let's say you run your torch.compile, you have your model, and this is not a vLLM model. Actually, this is a model from IBM that we've been running to test all this page attention kernel code before making the PR to vLLM and contributing the code back. But the idea is, does all these things that I was just talking about work, right? And then, as you can see here, you see some Triton code, Triton kernel being run on top, which is, in this case, I think it's the rope embeddings, in case you're familiar with that, what that is. Then we're calling the reshape and cache, which, there's no like extra stuff going on here other than that. Then we're calling the page attention kernel itself. And then finally, we're calling a matrix multiplication, which is also like compiled by, the Triton compiler to make it hopefully efficient, although we had a discussion this morning in which we said that it's probably not the best. Triton is not, the inductor compiler is not the best at choosing the best matrix multiplications operations yet. But what does the performance of this look like, right? Well, the test I was running is on a batch size of 4, and I generated not a big batch, like only 256 tokens to begin with. And this is running on a 1A100 GPU and PyTorch 2.1 still. The actual machine is the AWS P4D, in case you're familiar with that. It's the one machine they have at AWS that has like 8 A100s, and I think it's like Ice Lake CPUs from Intel, if I'm not wrong, and like 1 terabyte of RAM or something like that. So what does compilation time look like? In this case, it's, again, as I mentioned, the startup time is still pretty bad. It's like 2 minutes just to compile this one model. The iteration time from the eager execution to the compiled execution for a single token generation goes from 96 milliseconds per token down to 30 milliseconds per token. And I forgot, but this is a Llama 7B model. So that would be like, in this machine in particular, for this particular model that I have, it is open source, so you can check it out, and I'll have the link in the last slide. But basically, this is a 2.5x speed up. If you only look at, this is from the beginning to the end of the not just the forward pass, this is like, I finish getting a token and I start getting a new token. This is like the full time, right? If you only look at the part that we're compiling, which is just the forward pass for the model, that time goes from 94 milliseconds to 30 milliseconds, which is even better. Like the issue is that there's some other limitations to the model that of course show more when you reduce this overhead, right? I did look at the memory requirements. They basically stay exactly the same down to the byte. So in this case, the torch compiler didn't manage to optimize any memory out, but it didn't add any extra memory on top, which is good. It means we're not losing throughput at all, because usually throughput is memory bandwidth limited, right? And then the main issue is that, as you see in this picture, this is like what the GPU, the bottom line is the GPU execution, what's being run in the GPU, and the top is what's being run in the CPU. As you can see, the CPU is pretty busy all the time. As you can see, the GPU is not that busy. So there's still further ways to like reduce CPU overhead. The vLLM folks will talk about it, but they went the other way around. Like the next step to do this is using CUDA graphs to further reduce the overhead from all these CPU operations and reduce it to zero, basically, because you only run one launch for a kernel instead of like launching every single thing from the CPU. But you can do it the other way, right? You can have CUDA graphs first and then add compile to it. In our case, we started with compile, and then next step is doing CUDA graphs. I just didn't have time to get it working before coming here today. But ideally, when you run with CUDA graphs, you will see that the blank space in between like each of these small blobs of actual computation in the GPU will get removed. Some other numbers that are not here on the slide, but I checked this morning, is the eager GPU time. So the work that you're doing in GPU on eager mode for PyTorch is 12 milliseconds out of those like 94. On compile, it's 9 milliseconds out of the 30. So there is still like, compile is adding some optimization on the GPU as well, even though like most of the optimization is coming from the CPU side. That being said, and because I'm running out of time, the conclusion is basically yes, the compiler can offer significant gains in performance, although it should be probably combined with CUDA graphs, especially for like smaller workloads like this. But it also is still very much in development, and these numbers will probably look different next month with like the nightly build, or like PyTorch 2.3 when it releases in like May or so. It will look very different from what I'm showing here. I'm sure like probably better because compiler keeps getting better. But yes, there's some issues, and then of course the vLLM got caught out on some of these issues, and then thanks to them getting caught up on that, we had like a case to like make to like some PyTorch developers to improve some of these things, and that's why we can get it working now, right? And why would you want torch.compile? Well, torch.compile, as I said, is very good because it lets you compile to different like backends, and that means that you can probably get a lot of support for like AMD or Intel or other CPUs and accelerators for a lot cheaper than it would be to like rewrite every single custom kernel that you have in your code for each of these different processors. Like vLLM does have a lot of custom kernels. Most of them are written in CUDA right now, and probably if compile can offer a similar level of performance, but also on like 5 different like accelerators, that's something that vLLM may be interested in, and everyone else here in this room should be also interested in, especially if you're part of the AI Alliance. You can check out this code. You can use the QR code and the link are the same, so use whatever you want. And then this particular work I just presented is in this branch. Feel free to take a picture so you know which branch to look at. There's also a PR open right now, which is called like page attention or something, which points exactly to the same branch. So yeah, I think that's it pretty much. Thank you very much, and I'm going to leave the floor to the vLLM folks.
So while we set up,
sure, yeah.
If you have any question for Antoni,
I'm here.
now is a good time to ask.
Yeah.
If not, after that, you can.
Yeah, I'll be here until 8 too. So, so the question is, which operations are being fused that actually get this speed up? In our case, it's the rope embeddings.
Which one?
The rope embeddings. All the multiplications and everything that are happening on the rope embeddings are getting fused into a single Triton kernel that runs like I think it was from 0.069 milliseconds to like 0.003 milliseconds. So a pretty like decent speed up. There was someone else here.
Yeah.
Yeah.
Yeah. Thanks. My question is, have you benchmarked the Llama 70B compilation time with torch.compile?
Yes, and I just ran it like 3 hours ago. So 70B on the nightlies from 2 days ago, which is the one I think I have on my environment right now, took about 6 minutes to compile.
6 minutes
Yeah.
on a P4D machine?
On a P4D, yeah.
Okay. Yeah.
That's from like this afternoon, so. Okay.
You mentioned that torch export could solve that first issue of the setup time.
Yeah.
What kind of were the issues that you faced with getting torch export working?
Yeah, so again, the question for like the recording is, what issues have I seen with torch export, and why are we not using this for like the setup time, right? So the main issue is that a lot of the function, like when you're trying to run Llama 7TB, for example, there was almost no support for all the all reduce and all gather and all these different collectives that you have to run on to run like any tensor parallelism in Llama 7TB, for example, or any other big model, right? There was no support for that. I think they landed the support for that recently, so I need to try it again and see if that works. I just haven't had the physical time to actually go and try it again. Yes.
I'm wondering, how does your work handle dynamic batch sizes? Are you using the torch native dynamism support, or are you doing some padding scheme?
Yeah, so this question is about if all these I just presented does support dynamic shapes for compilation with vLLM, and the answer is yes, it does. And it just works with torch.compile.
So for more questions, catch Antoni later.
Yep. All right, thank you very much. And I'll go to the next part.